Thank you, Professor Sally, for that really wonderful and quite informative talk. You really covered a lot of topics and areas related to air pollution and aerosol. I'm sure it is quite inspiring for many of our audience members, especially the ones who are starting their career. So we have a few questions. I'll just get to them. So starting off with, so could you shed light on the size distribution of aerosols and how does the particle size impact the health and climate impacts of aerosols?
So that is a very great question. So for the Ascent network, we have an instrument that measures the size distribution of aerosols. This is the scanning mobility particle sizer. So for a lot of the aerosols in the Southeast US, they are actually in PM1. So EPA regulate PM 2.5, which are particles smaller than 2.5 micron. But we have done measurements for PM1 and PM 2.5 here in the Southeast US, and we find that there's actually a lot of the PM 2.5 is in PM1. So if you're measuring PM1, you're mostly covering the PM 2.5. But this is actually not the case for maybe other places in Asia. So there have been studies coming from China to show that there's actually quite a lot of aerosols between 1 and PM 2.5. So I would say that this is pretty characteristic of different places around the world. And so I would urge everyone that if you have a capability to measure both 2.5 and 1, so for example, this aerosol chemical speed station monitor, it has a lens, an inlet. So you can change it. You can measure PM 2.5 or PM1. And so that's what we did. We actually employed two instruments side by side. One measures 2.5 and one measures 1. And that would allow us to learn about the composition and the size distribution of the different aerosols in different size bins.
Thank you, Professor Sally, for that answer. I'll move on to the next question. So considering aerosols are of complex shapes and morphologies, what does size exactly mean for aerosol?
Yeah, so I guess like size, I should have a slide on that. But so the size we think of aerosols, like aerosols comes in different shapes, right? But typically, if we assume that it has a spherical size, right? And so the size will mean that it is just a sphere, right? So it's the diameter of the aerosols. So our hair is about tens of microns, so it's much bigger than the aerosol. That's why you don't see them. And so if we are thinking of aerosols, typically of the three categories we think about is PM10. PM 2.5 and PM1. So PM10 is obviously particles with 10 micron in diameter, right? So the PM10 aerosols will be a lot of them got trapped in your nose, and so it could not go into your body. But the PM 2.5 and PM1 aerosol, they are very small. So they can go through your nose hair and go all the way deep into your lung and cause different health effects. And so that's definitely like an impact of the size on health, because if the aerosols are too big, they settle or they got trapped by your nose and they would not go into your body and harm you. But these particles we are talking about is very small. It's like 1 micron, 2.5 micron, and so they go very deep into your body and cause different health effects.
Thank you, Professor Sally. So the next question is, which sources contribute more to the aerosol budget? Is it biogenic or anthropogenic activities? Or is there a clear difference? Do we have the exact answer for that?
So the answer would depend on where you are. So I spent, I guess, more than a decade in the Southeast US now. So I can tell you that in the Southeast US, we have a lot of contribution from trees. So basically, this is the answer to the question, right? So in terms of what are making the aerosols, what is contributing to the aerosols? So we have a lot of organic aerosol. So this is true pretty much everywhere around the world. Like we have, there's some sulfate aerosol. So sulfate aerosol is from power plants, right? But as the, coal-fired power plants, going down, then there's also less sulfate aerosol. So what is becoming first the dominant contribution of aerosols is the organic aerosol. And if you made this charts in different parts of the world, you will see that organic aerosol always comes out to be one of the major parts of the composition. And then once we do the source apportionment analysis, it tells us what is the contribution of different types of aerosol, right? So here you can see the cooking aerosol is about 20%. So this measures in Atlanta. But if you're measuring in even cities with more restaurants, then you can have bigger contribution from cooking aerosol. And then the big question that I think the community should think about is what is this OOA? Because again, no matter where you go in the world, you're going to see a huge fraction of OOA. It doesn't matter if it's LO or MO, but you're going to see half of the pies or half of the bar charts are going to be this OOA. And this is the challenging question because cooking aerosol is cooking aerosol, but what is OOA? And the answer depends on where you are. So in the last decade, we have done a lot of measurements here in the Southeast US to show that the LOOA has a lot of contribution from trees, from monoterpenes. But the question is, what about your area? What is your LOOA? And so that requires a lot more measurements in terms of using these mass spectrometer analysis and also combined with laboratory studies to really integrate field and lab studies to answer this question. So I would say that this is one of the major scientific challenges for the young researchers maybe in the audience to think about, in terms of what is the source of these oxidized aerosol in your area. You're muted.
I'm really sorry. I was just saying, like, to build upon that answer. So you said, like, we need more measurements, more data points. So we had one question. So you shared that field-based equipments or instruments are, like, say, aerosol mass spectrometer. They are quite expensive. So are there alternatives for monitoring aerosol composition in different regions with, say, limited data availability and economic constraints?
Yeah, so the aerosol mass spectrometer is quite, I would say, pricey. And so that's why we developed this aerosol chemical speed station monitor, which is still not that cheap, but it's much cheaper than the aerosol mass spectrometer. So that is kind of really to address this question, is there's an instrument that can be used for routine monitoring of aerosol composition, right? So that's why we started the Ascent network, because all of these instruments is expected to be running on their own, right? You don't want an instrument that you have to be there every day and calibrate it every day and play around with it every day. For long-term measurement is not practical, right? So in terms of this Ascent network, we selected these 4 instruments such that they are capable of more routine measurements at a remote site. So we have different sites in the middle of nowhere, right? So these instruments should be able to run at different sites for long-term and routine measurements of aerosol composition. So I would say that right now, like the ACSM is still I would say, only major instrument available that allows for real-time monitoring of the aerosol chemical composition. And it's pretty robust, and it allows us to also gain this similar type of information as I'm showing here. So we have been, collecting data from the Ascent network for a year now, and we are learning about the different composition of aerosols, at all the different sites. So I know that there's a lot of audience here from India, right? So I think this will be something to think about, for the country, because different places in the country can have different sources of aerosol. So if there's capability to form this network in India, that will be wonderful to really learn about the aerosol composition and their impacts on climate and human health.
Definitely. Thank you, Professor Sally. I mean, India can definitely use some of those not even high-end equipments, more data points, so to say. Thank you. Coming to the next question. So in your slide 2, if I'm not wrong, you showed high uncertainty associated with radiative forcing of aerosols. So does the height of the aerosol in the atmosphere, say troposphere versus stratosphere, does that affect the radiative forcing?
Yeah, so in terms of the aerosols, a lot of them are depending on the size and the composition, right? So in terms of the light scattering, different sizes of aerosols will scatter, absorbs lights differently, so their size really does change, the radioactive forcing. And the second is the composition, because you can see that these brown carbon that I was showing maybe in the later part of my talk, right? So the brown carbon are really brown, so they absorb the radiation. I always tell my students, my hair is black, so it absorbs, radiation a lot. So you have black carbon, brown carbon, it absorbs radiation and warms the earth. But if you have sulfate aerosol, actually, at this slide, at the beginning, right? So if you have a sulfate aerosol, so this is a volcanic eruption, right? So volcano eruption produce a lot of sulfate aerosol. So sulfate aerosol is actually cooling because sulfate aerosol reflect radiation, back to the space, right? So in terms of climate engineering, there's quite a bit of interest in, injecting particles into the stratosphere to reflect, the radiation, back to the space. But this is I would say, major scientific, society, policy questions because it's not something that you do in one area of the world and it just impact where it is. It would impact, the whole world. So I think a lot of research should be going into, understanding the consequence of this. And I'm not sure if, one day we'll get into the future that we really have to, implement this. But I do think that the scientific study should be conducted just to gain more understanding of these type of, I'll say, interventions.
Really important. Thank you, Professor Sally. We are almost on time. Is it all right if I take a couple of more questions? If you can spare some more time.
Yeah, sure. I have time. Yep.
Thank you. Thank you, Professor Sally. So moving on to the next question, you shared that there are approximately 8.9 million deaths worldwide that are attributed to ambient fine particulate matter. How is this figure exactly estimated? Like, how do they get this number?
Yeah, so they have so first of all, these are a lot of epidemiological studies, right? So it's a big scale population level studies. So they always have models to estimate the PM2.5 concentration. And then they have a response function in terms of, per microgram of PM2.5 would cause, this much, health effects. And so this is mostly a epi study, and so what we are interested in doing, as I show in the last part of the talk, is also linking the studies to more of a toxicology mechanism, right? In terms of how the different aerosols will be toxic in different ways. So right now, the EPA regulation, and actually everywhere, the whole world's regulation is PM2.5. Right. So then the question is, what if the different parts of the PM2.5, like PM2.5 is different compounds, right? Different particles. What if different types of PM2.5 or different aerosols have different toxicity? Then does it make sense to actually assign the same toxicity function to all PM2.5? Right. So I think this is something that we are very interested in doing, is to try to link the chemical composition of the aerosol to their health effects. For example, I'm just making an example, if you have an aerosol, cooking aerosol, maybe it's not as toxic as wildfire or aerosols from vehicle exhaust, then maybe we should not regulate the non-toxic aerosol that much, but spend more effort, regulating the sources of aerosol that is more toxic. So while at the meantime, without a deeper understanding or a standardization of the toxicity assigned to different type of aerosols. Right now, we are just treating, all the aerosols have the same toxicity. And this is based on, like most of the epi studies are building on this, is that, we just treat, all the aerosols as the same. But I do think there's a need to really start thinking about the toxicity of different types of aerosols, not just PM2.5 mass as a whole.
Thank you, Professor Sally. Moving on to the next question. I'll just take a few more. So what is the source of hydroxyl radicals in the atmosphere? And do you think like the levels of these hydroxyl radicals differ globally?
Yeah, so hydroxyl radicals, so there's the water photolysis, and they will react with ozone, and then you make a lot of OH radicals. And so the OH radicals is always considered as, the cleanser of the atmosphere. So they are very oxidizing. So basically, like if I look at this slide, oops. So this is the OH radical, right? So OH radical is the most important oxidant together with ozone during the day. And so they can oxidize many different compounds. So ozone can only oxidize compounds with a double bond, but hydroxyl radical is not picky. Hydroxyl radical can oxidize double bonds, can oxidize single bonds, and so they are very oxidizing. And many of the VOCs, when they get oxidized by hydroxyl radicals, they can turn into products that have different volatility. And so I'll say that, together with the hydroxyl radicals, ozone and nitrate radicals, there's different oxidants during the day and night. So during the day, mostly will be hydroxyl radical and ozone. And at night, you don't have hydroxyl radical because there's no photolysis. And most of the time is oxidized by ozone and nitrate radical. And depending on, even you have the same VOC, if you're oxidized by different oxidants, you also make different, aerosols, and they can have, different composition and impact on climate and human health.
Thank you, Professor Sally. I'll just take the last question. It's more of a general question, not exactly related to your presentation. But so there are many plantation drives. So what is the impact of these plantation drives? These are popular measure to contain global warming or reduce pollution and its impact on air quality. What would be your comment on that?
So is planting, I guess, trees like more of a some sort of
yes. And there are many drives like that, hundreds and thousands of trees in one go.
Yep. So that's a very interesting question. Like because trees does a lot of really wonderful things, right? They take in the CO2 and cleans up your air. It looks nice. But one thing to consider is that what is next to the trees, right? So like a tree planted in Atlanta will be different from a tree planted by in India because the environment will be different. And so the story that I show here is that when you have trees planted next to traffic. With these vehicle emissions, then you form a lot of organic nitrate, and organic nitrate can be photolyzed to release that NOx and then form ozone, right? So one thing is that actually from this story, I didn't get a chance to talk too much about is that you don't want to cut the trees. The trees are good, right? So how do you reduce the amount of aerosol from trees? Then you can reduce the vehicle emissions, right? Because this is kind of a way to control the aerosol formation from trees is that if the aerosol formation from trees is linked to vehicle emission, if you reduce the vehicle emission, you have the side benefit of actually reducing the aerosol from trees. And then another consideration, so planning, where to plant the trees is an important, consideration. Maybe you should not, plant next to the highway or plant, somewhere else. And the second consideration is the type of trees to plant, right? I think some consideration needs to go into what type of trees to plant because different trees will emit different volatile organic compounds. So maybe in terms of planting trees, the committee can spend some time thinking of planting trees that are good for the soil, for the air, for the community, but at the same time maybe select trees that does not produce many of these VOCs that can react with hydroxyl radicals to make aerosols. So I think there's quite a bit of thinking that can go into, in terms of where to plant the trees and what type of trees to plant to reduce their impact on adverse impact or unintended, impact on the environment and the climate and the human health.
Thank you so much, Professor Sally, for answering all those questions. I'm sure it was very helpful for all the audience members. So any last comments for the early career researchers and the PhD students in the club? So any leaving comments?
Yeah, so I would say that, like hopefully, everyone who's, joining today's presentation has a passion, for the environment and really doing something good for the world. And I think we are living in a very challenging time in which, air quality and then climate change continue to really impact in the world in major ways. And so, I urge you to, work hard and use your passion to really contribute in our understanding of reducing pollution and also, really help fight the climate change, battle. And there are a lot of different tools, a lot of different resources, available. And also there's importance for collaboration, across different parts of the country, collaborations, across the world. And so I really encourage you to find, there are many topics you can study in terms of even just air quality, climate, and human health. And so really identify the topic that you're the most passionate about, and devote your time and effort and ask good questions. And I think that will take you far. So, when I was a student, I didn't, I was trained as a chemical engineer, so I did not know too much about, pollution. But during my study, I got experience to do undergrad research at the Hong Kong University of Science and Technology. And then that really introduced me to this area. And so it allowed us to use my chemical engineering knowledge to understand, air pollution. And so I think this is a really interdisciplinary research area. So it doesn't matter which, discipline that you come from. I think there's an opportunity for everyone to really, contribute to addressing these major global challenges.
Thank you, Professor Sally. Really great message. Over to you, Krishna.
Thank you, Ashish, for that wonderful Q&A, and thank you, Professor Sally, for that wonderful message. And the way you really handled all the questions, it was really insightful. So I request you to kindly stop sharing. Thank you so much. With this, we come to the end of today's session. I really hope that you enjoyed this broadcast. We invite you to view the edited recordings from the past events in the ACS Science Talks library. At the end of the session, all our attendees, they are going to receive a brief survey. We request you to share the feedback with us so that we can continue to improve and serve you better. On behalf of everyone, thank you all for joining us today. We hope to see you soon for more ACS events. Until then, stay safe and stay healthy. Thank you, Professor Sally, again for joining us. Bye-bye.
Thank you. Bye-bye.